you for joining me. I'm glad to have you here. Today I want us to look at simple harmonic motion. Just quickly before we start, if you have not subscribed to this channel, feel free to hit the subscribe button, give it a like, and then share this video with your friends. Thank you. Now, simple harmonic motion is nothing but the to and fro motion of an object. Now, this to and fro motion of an object, remember, must be directed towards a fixed point. So, the motion of an object that is directed towards a fixed point, of course, not everything is directed towards a fixed point, the acceleration. So, we cannot say that, yes, a body is said to undergo simple harmonic motion when the acceleration of that body is directed towards a fixed point. Or, we can say that, yes, a body is said to undergo simple harmonic motion when each distance from the center is directed towards a fixed point. And of course, we know that, yes, if a body is undergoing simple harmonic motion, let's say if this is the motion of a pendulum bob, it is moving to and fro. And then if it moves to this point, let's say from point A to point B. So if it moves to A to point B and then come back, this bulb is directed towards a fixed point. So it is fixed. That means we now say that, yes, a body is said to undergo simple harmonic motion if its acceleration is directed towards this fixed point. Now, we can give some examples of a simple harmonic motion. One of those examples is the motion of a simple pendulum, or motion of a pendulum bob, or motion of a pendulum clock. You know how it moves, to and fro. That is number one. Another thing is the motion, the beating of the heartbeat. Remember, it is consistent. It is consistent. So that's why when I say the heartbeat is one of them. Another one is once after washing your clothes, hang it on a rope. It starts to move back and forth. Of course, with time, it will come to a halt. So that also is another example of a simple harmonic motion. We can have a loaded test tube oscillating vertically in a liquid. If you load a test tube and allow it to oscillate vertically in water or in a liquid, so it is also another example of a simple harmonic motion. Remember, not always this simple harmonic motion can also move in a circular orbit. Example, if I tie this marker to a rope and then whirl it around, if you whirl it around, it moves in a circular orbit. Of course, it is still an example of simple harmonic motion. Now, we discuss some terms. Let us look at some terms that are used in describing simple harmonic motion. Those terms are, we can have amplitudes. Amplitudes represented with A. We can have frequency, or let's say period first. Periods represented with capital letter T. And then we can also have number 3. We can have frequency represented with F. Now let us take them one after the other. Remember, if a body is moving either up and down, back and forth, or to and fro, it can be represented like this. It can be represented pictorial. This is y-axis. Let's say this is a time axis or x-axis. Let's use x here. Now, if this body is moving up and down, we can use this sinusoidal curve to represent it. up and down, up and down. Now this is, at this point, the body is at rest at this point. Now, if the body moves up and get to a particular value, it cannot exceed here. Since it cannot exceed here, this is the maximum point. And if it's coming down, it cannot exceed here. So if you measure from here up to here, so this is our amplitude. So from here to here is our amplitude, or from here to here is our amplitude, however you want to put it. Now, by definition, we can have that the amplitude of a simple harmonic motion is nothing but the maximum displacement of a body from rest position, because this is a rest position. Maximum displacement of a particle from rest position. Now, we can now look at period of a simple harmonic motion. Now, period, of course, if a body is moving up and down or sideways from A to B and then back to A. So from A to B is just half a cycle. Now if it returns back, it is one complete cycle. In other words, from A to B can be represented with this loop here, while from B to A can be represented with this second loop. So this is the forward movement and then the backward movement, or back to its original shape. Now we can now say that period of a simple pendulum is the time taken for a body to make one complete oscillation. From here to here is half, from here to here is another half. So half plus half is one complete oscillation. So time taken for a particle to make one complete oscillation is what we regard as a period. Now we look at frequency. Frequency is defined as the number of oscillations a body completes in 1 second. Now if you look at this, this is half oscillation, this is another half, half. If you keep counting, half here, 1, 1.5, 2, 2.5, 3. So this is 3 cycles or 3 oscillations. So number of oscillations performed over time. So we now have that F is number of cycles over time. Number of cycles over time. So which will give us that F is N upon T. Let us go back to period. Period T is, remember we said it is a time taken for a body to make one complete oscillation. So time taken all over the number of oscillations, all over number of cycles or oscillations. Cycles or number of oscillations. Therefore, we can now have that T is small t all over n. So we have this as the first formula, and then we can have this as the first formula. If you look at this now, something is common here. We have t and n here, t and n here. Now, when t is n here, when n is on top, t is down. Here, t is up, n is down. It means that this one is inverse of this. Why this is inverse of this? Therefore, we can now say that t is 1 over frequency, while frequency here is the inverse of period. So this is another formula. This is another formula. Now we can do with this formula. Let us take 1 or 2 calculations to add the flesh to what we have just discussed. Now we take this first question, and this question says a simple pendulum makes 50 oscillations in 1 minute. Determine the period of oscillation. Now solution. From here, number of oscillations here, n, which is the number of oscillation. Number of oscillation is 50. Now the time for the oscillation is 1 minute. And I said determine the period, t. One thing we have to do here is to convert this. And of course, if we are moving from minutes to seconds, you multiply. If you are moving from minutes, sorry, if you are moving from seconds to minutes, you divide. So in other words, since we are moving from minutes to seconds, we now say 1 minute times 60 seconds will give us 60 seconds. Now we now have that period of oscillation is small t all over n. Remember, not the other way around. If you send it on up, it becomes frequency. So we now have that. Now time is 60 all over n. N is 50. This over this will give us 1.2 seconds. So this is the periods of oscillation here. Let us take a second question. Okay, we take the second question, and this question says, a boy timed 20 oscillations of a certain pendulum 3 times and obtained 44.3 seconds, 45.5 seconds, and 45.7 seconds respectively. Calculate the mean period of oscillation of the pendulum. This question, you need to understand this question before you solve it. The question says, a boy performed a particular experiment, and the experiment was performed 3 times. And of course, when you perform it, even if you perform it 10 times, you will still get 10 different values. Maybe you can have a concordant value, very close values. Now he said he did it the first one T1, did the second one T2, did the third one T3. So the first one he got 44.3 seconds. The second one he got 45.5 seconds, and the third one he got 45.7 seconds. Now that's it. The period of oscillation, the mean period of oscillation, this is the key word here. Mean period is oscillation of the fact time taken for a body to move from, let's say, point A to point B and then back. Time for one oscillation. That is what you are required to get. So we now have, what do? Get the mean. Take the average of this. T mean is T1 plus T2 plus T3 all over the number of values there, which is 3. Which will now give us, T mean will give us, T1 is 43.3 plus 45.5 plus 45.7. Everything divided by 3. Now, if you punch your calculator there, you have 43.3 plus 45.5 plus 45.7. At the end of the day, you will get that T mean is equal to 134.5. Now, if you divide it by 3, the average of the time there will give us 44.83 seconds. That is the average. Now, having gotten our average to be this, the number of oscillations, number of timings there is, what that means, N is 20. T mean is 44.8. At this point now, you can now calculate your mean value. Period will now give us T mean all over N, which will give us, the T mean is 44.83 all over 20, which will give us that the period of oscillation there will give us 2.24 seconds. That is the period of oscillation of that body. Now we'll take the last but not the least question. Now we take this question. This question says, 2 simple pendula X and Y makes 400 and 500 oscillations respectively in equal time. If the period of X is 1.5 seconds, what is the period of oscillation of Y? What is the period of oscillation of y? So, solution. This question, you need to be careful with this question. Here, there are two pendula here. Pendulum X and pendulum Y. Now, this one has the number of oscillation for X. We can use LX to represent it. Is that first value there, 400. While the number of oscillation for Y is 500. Then said the oscillations were done in equal times, small letter t. T for X is unknown, T for Y is unknown. They rather gave us the period for X to be 1.5, and then they asked us to get the period for Y. Now, from here, since these two are given, we can use the two of them to get Ty using Tx, using T is equal to number of time of oscillation all over number of cycles. So since we are looking for X, we put X here, put X here, and put X here. And when that is done, we substitute. Here is 1.5. Now Tx is what we're looking for. We're looking for Tx all over number of oscillation. The number of oscillation here is 400. At this point, we can cross multiply. If we cross multiply, Tx is equal to 1.5 times 400. So Tx will give us, you will punch your calculator, 1.5 times 400 will give us 600 seconds. Remember, they said that both of them were done in equal time interval. That means Tx is equal to Ty, and everything is equal to 600. That means we have gotten our Ty. Ty, we can clean here to write 600 here. So with these two, we can find the period of oscillation for Y. Using period of oscillation for Y is equal to time of oscillation all over the number of oscillation for Y. If we substitute, we have time of oscillation for Y, which is same thing as time of oscillation for X, is 600 all over the number of cycles or number of oscillations. Number of oscillations for Y is 500. And of course, from here we can cancel. Therefore, period of oscillation for Y, to punch your calculator, 6 over 5 will give us 1.2 seconds. So we have, from here, we have been able to get the period of oscillation of Y. So at this point, this is where we'll draw the lesson to an end. Please, if you have not subscribed to this channel, feel free to subscribe to this channel, hit the like button, and then share this video with your friend. Moreover, we have an online platform. If you need more clarification, we have an online platform. Check the description down below or in the comment section. There is a link there. Click that link and then join us so that we'll be having a live lesson. See you. Thank you very much.